Let's look at the general form of Gauss's method. This will be important when we want to prove that Gauss's method is safe and successful. Okay, so a linear equation is made from linear combinations. So here's what a linear combination is. We have n variables, x1, x2, x3, x4, up through xn. And with each variable, we have a constant called its coefficient. A1, A2, A3, up through AN, and we form terms, that is A1, X1, A2, X2, A3, X3, up through AN, XN, and add them together, and that forms our linear combination. And the constants can be any or any values that are chosen for the real numbers. Okay, here's an example with a linear combination of x, y, and z, where the coefficients are 1/2, implicitly 1, and implicitly -1. Okay, here's how to use a linear combination to make a linear equation. Put the linear combination on the left and set it equal to a constant, the constant d. And the variables in the equation are the same as the variables in the linear combination. And here's an example. The same example as before with a linear combination above equaling 12. Okay, so what are the solutions of such an equation? Well, an n-tuple, that's a list of n values, of n real numbers, s1, s2, s3, sn, is a solution of or satisfies a linear equation if substituting the numbers, the values, s1, s2, up to sn, for the variables x1, x2, xn, produces a true statement. Because an equation is either true or false, and a solution is the set of values that make the linear equation true. For example, the previous linear equation from the previous page, 1/2 x plus y minus z equals 12, has the solutions listed. You take the first one, 1/2 times 4 is 2, 2 plus 10 is 12. The third one is just y is 12 and equals 12. And of course, there's many other solutions. Now, we'll be interested in writing the set of all solutions. And this is the form that such a set takes. It's not very insightful, but it captures what's going on, the logic of the set. S is the set of all the solutions. That is, it's the set of all the n tuples, the lists of n real variables, such that, that's what the vertical bar means, that the linear equation is true. So linear equation acts as a test to determine whether a given n tuple is a member of the solution set or not. Okay, so finally we come to the object of the present enterprise, which is the linear system. And the linear system is formed from a list of linear equations. Now, each equation has to have the same number of variables, even if they're not explicit, they're there, maybe with 0 coefficients. And we have here, so we have the first linear combination equals D1, the second linear combination equals D2, down to m linear equations. We don't have to have the same number. We could have more equations than variables or fewer equations than variables. And the coefficients now have to have an extra index. On the first row, you can still see in the second index 1, 2, 3, up through xn, whereas the first one, if you read down the first column, they're going down 1, 2, 3, m. So the first index labels the equation, and the second index labels the variable in that equation. And again, a linear system has a solution, a set of n variables, if this is a solution of all the equations. So if I plug in the S1 through Sn for all the x's in every equation, they all become true. Okay, here is an example of 3 linear equations with 3 variables. Here's another linear system with 3 variables, but only 2 equations. Now, the goal of Gauss's method is going to be echelon form. Now, if we look at one of these linear systems, we can look at the first variable in any row of a linear system. The first row of in any row of a linear system, that's in any equation, is the leftmost variable with a non-zero coefficient. Okay, A system is an echelon form when the first variable, that's the one that's leftmost in a row, is to the left of the first variable in all the rows below it, and all 0 rows are at the bottom. What this means is, if I start from a left, for example, in the first row with a leftmost term, there's going to be no non-zero terms underneath it. And if I go to the second row, there's going to be a leading term there, and it'll have nothing underneath it. Okay, so for a system, once it's in echelon form, the first variables, those leftmost with a non-zero coefficient in each row, are the leading variables of the system. Those variables that are not leading, that aren't the leftmost ones in a row, are said to be free. The goal of Gauss's method is to find an echelon form version of the original linear system. Okay, here's some examples. Is this system in echelon form? Yes, it is. Because the x is the first term in the first equation, and it has nothing underneath it. It's to the left of the z that's in the second row, and the z has only 0 entries below it, so this is in echelon form. Is this second form, the second system, in echelon form? Well, the x has nothing beneath it, and it's to the left of all the leading entries of the lower rows. But when I come to the lower rows, on the second equation, the y, which is the first variable on the left, the leftmost variable, it does have something underneath it, another y term, so that the first variable in the second equation is not to the left of the first variable in the third equation, so this is not in echelon form. The first variable in the second row has a term underneath it. Okay, that's it.